This section covers schema and row key design in Bigtable. This slide introduces the components of the schema in Bigtable. Let's start by focusing on an example layout of a table in Bigtable. Here we have an example table with generic labels. We have a row key on the left-hand side in the red, which uniquely identifies each row in the table. Next, we see the table is split into column families. These are A and B in this case. Each column family acts as a container for columns. And within column family A, we have three columns, column 1, column 2, column 3. Similarly, in column family B, we have two columns, column 1 and column 2. Now, notice that each row, defined by its unique row key, does not necessarily have data in every column. If you look at row 1 and row 3, you'll see that some columns don't contain values. This demonstrates that in Bigtable, you don't actually need to have data in every column for every row. And Bigtable tables are actually sparse, where empty cells don't cost any storage. This is different from those cells just being null and the null value showing up as the value of the column in that row. It actually doesn't cost any storage and the cell is truly empty. Now let's turn to some bullet points and understand how this structure works in Bigtable. Column families group columns together. Each column family acts as a logical group to manage related columns. Columns exist within column families, but they're defined dynamically based on the data that's written. This means that columns don't need to be the same for each row. For example, one row might have data in column 1, but no data in column 3, and that's perfectly fine in Bigtable. Bigtable tables are sparse, meaning that empty cells don't cost any storage, as I just mentioned. So the table can store different types of data without wasting space, and there can be some cells that don't have any data and that won't cost any storage. Row keys are the unique identifiers for each row. These are important because they determine how your data is organized and accessed. And finally, only the row key is indexed in Bigtable, which means that the design of the row key is extremely important for performance, and we will be going over how to design good row keys. Let's look at an example table of actual data, in this case stock data. So this is an example of how a Bigtable schema might look in a financial context where we are tracking stock data for different companies. The row key represents the unique identifier for each row, as we've already established. In this case, it is the ticker symbol for each company. So AAPL for Apple, GOOGL for Google, and AMZN for Amazon. This row key allows us to quickly locate all of the relevant data for that company. Now let's look at the column families. In this example, we have two main column families. The first is prices, which includes multiple columns, opening, closing, and high. These store the daily stock price data for each company. The second column family is volume, with columns for volume traded and average daily volume. This captures the trading volume for the stocks. And for each company, we have different values for these metrics, and the row keys organize the data for quick lookup. One key thing to note, though, is how the schema is flexible. For example, if one day we wanted to add a new column like low price, we could easily do that without predefined schema limitations. So I just wanted to show kind of a real world example. This highlights how Bigtable's schema, especially how dynamic it is, allows us to add or change columns as needed, while the row key gives us a fast and efficient way to access data. Let's talk about hotspotting. Hotspotting is a performance bottleneck that occurs when too many requests are sent to a small subset of nodes in the Bigtable cluster. This usually happens when the row key design didn't lead to an even distribution of data across the nodes. Let me walk you through a visual on this slide in order to explain the concept. On the left side, we have what you would call an ideal scenario. Here you can see a client represented by the terminal icon. It is sending requests to the Bigtable cluster, and the arrows show that these requests are evenly distributed across the available nodes. Each node gets a fair share of the requests, allowing for balanced performance and reducing the chances of any bottlenecks. Now, if you look at the right side, you'll see a bit of a different situation. This indicates hotspotting. The same client is making the requests, but in this case, notice how a disproportionate number of the requests are hitting just one of the nodes, while the other nodes are being underutilized. This leads to a bottleneck because a larger number of requests are being sent to a single part of the cluster. The data is not spread out properly across all the nodes, which means that the system can't fully take advantage of the distributed architecture. This uneven distribution is often the result of a row key design that leads to clustering of related data on just a few nodes. Common culprits of hotspotting include using sequential timestamps or similar patterns as your row key. It can lead to more frequent access to just a small subset of nodes like we see here. In general, sequential numbers are not a good idea for hotspotting, or for the row key. It can introduce hotspotting. And that's the essence of this concept. It has a pretty good likelihood of showing up on the exam, so make sure that you understand this. We'll go over some techniques to deal with it as well, but this is the underlying concept. It is an imbalance of request distribution that strains certain nodes while leaving others underused, and this affects overall performance of the cluster. When designing your row keys in Bigtable, it's helpful to consider a few best practices to ensure efficient data distribution and avoid performance bottlenecks like hotspotting. First, use a reverse domain name. This is a best practice in your row key. Instead of a typical domain format like www.mywebsite.com, you would reverse it to com.mywebsite.www. That can help distribute your data more evenly across Bigtable. If you reverse it like that, entries starting with a different top-level domain like .com, .org, .net, they will spread the data more evenly across different parts of the cluster, and this ensures a more balanced distribution. This strategy ensures that the data is more evenly spread across the cluster because it randomizes where data lands, reducing the likelihood of concentrating too many requests on the same part of the cluster. So a domain name is an easy example of this, but really anytime you have some kind of data with a prefix, a middle part, and a suffix, insofar as you can choose to put up front the part that will vary between rows, that will help to distribute it across the cluster. Next, you might want to use timestamps at the end of the row key or reversed timestamps. For example, in a row key like this one, the timestamp appears at the end rather than at the start, which helps to prevent hotspotting. If you put timestamps at the beginning of the row key, recent data can be bunched together, and this causes the same part of the cluster to receive more traffic. By placing it at the end or by reversing the timestamp, you spread the data across more clusters and maintain better load balancing. So if you think about it, the part of the timestamp that changes most frequently when you have a regular timestamp is the end of the timestamp, right? So then if you put that up front in the beginning of the row key, it's almost like we're doing the same thing as reversing our domain name, where the more variable part of the row key is up front in the beginning. Another useful approach is employing string identifiers like this taken from our example, AAPL, which is the stock for Apple. String identifiers are a good choice because they are unique and they do not follow a sequential pattern, which helps to distribute data evenly across the system. Now, similarly, let's talk about row key designs to avoid. First, avoid using domain names that are not reversed, such as www.mywebsite.com. Without reversing, similar domain names will be clustered together. A lot of them will have www up front, and this will cause uneven data distribution and potential hotspotting. So then, by reversing them, as mentioned earlier, you can help spread the data more evenly across the cluster. Second, be cautious about using sequential numbers in your row keys, such as the ones here. Sequential row keys can cause Bigtable to store data in a lexicographical order, and this results in an uneven distribution where certain regions are overloaded with traffic. Lastly, steer clear of keys that involve frequent updates, like in this case, user123 underscore balance underscore 1500. So in this case, we would be updating, we have included the user's balance, which in this case is 1500, in the row key. And although you do want to sometimes combine multiple columns into a row key, this can lead you to have to update the row key very frequently, like if their balance is changing frequently, and that can create operational inefficiencies. Really, the balance should just be a column in this case. Keys that change often can create serious performance issues, especially if they're being updated frequently in real time. It can increase load on a specific area of the cluster and just reduce overall efficiency. Another technique for preventing hotspotting is called salting. Let's go through an example. On the left, we have a set of row keys, user 001, user 002, user 003. Without any modification, these are sequential, and so they might cause hotspotting. They will be stored in close proximity to each other within the Bigtable cluster. If a large number of read or write requests target these rows, they will all be routed to the same part of the cluster, maybe the same node, and this creates a bottleneck. So imagine, though, if we added a random prefix, like 3 or 7 or 2, to these row keys. What would this do? It would spread the data more evenly across the nodes in the cluster. The new row keys, like 3 underscore user 001 and 7 underscore 002 and so on, are no longer sequential. There's no pattern to these. So the requests targeting them will be distributed more evenly across the cluster, and that avoids hotspotting. The technique of adding a prefix is called salting. And salting adds a random prefix to row keys to spread data across nodes more uniformly. We just saw this in the diagram, but it really can be a number. It can be some other prefix. The point is that it should be random. They are usually random numbers or just hash values. You don't need to pick a specific number. A system-generated number or hash value works well to distribute the row keys across different parts of the cluster. And just some considerations. It can complicate range queries because row keys are no longer stored sequentially. So if you have a lot of range queries, basically where you need to query a range of users, based on the values of their row keys. The row keys with prefixes won't be in a predictable order, so it can, for those specific kinds of queries, it can reduce the performance. It also does increase a little bit of overhead because you obviously have to modify the data on ingestion and then account for prefixes when you are querying the table. So salting is a powerful technique to prevent hotspotting, but you should consider these additional factors, especially when performing range queries. Another thing you need to know about regarding row key design in Bigtable is the technique of field promotion. Again, let's start with an example to illustrate what this is. In this row, we see a row key, sensor 123, along with the columns in the weather column family, which include timestamp, temperature, humidity. The timestamp is stored as its own field, representing when the data was collected. And this is typical before field promotion. Now, at the bottom, we see what happens after field promotion. The row key has been enhanced with the timestamp. So essentially, this new row key combines both the sensor ID and the timestamp directly in the key itself. This means that the timestamp is now part of the row key rather than being stored separately as a column. This moving of the timestamp into the row key avoids having to perform a full table scan when querying for records by both sensor and time. Instead, the row key, which is the part that is indexed, allows for much faster and more efficient lookups. And so to summarize this, moving important column data to be part of the row key, such as the timestamp in this case, can enhance query performance because the row key is what is indexed, and so it can be queried directly. This action is what we call field promotion. Field promotion allows us to reduce the need for full table scans by incorporating important query fields directly into the row key. And the only catch to this is that it needs to be carefully planned to balance the benefits of optimizing reads with the impact it can have on write performance and overall complexity. Let's talk about the key visualizer, which is a tool in Bigtable that you can access through the console. This is an image that Google has included in their documentation. I know it might look like a lot, but we're going to break it down. As you can see, it's essentially a heat map. On the left side, we have these gray rectangles, which are row key prefixes, and they can form a kind of hierarchy, as we see here. This helps us to identify the distribution of data across the key space. In terms of the colors, the purple areas are the regions with few or no operations. So these are parts of the table that are not being heavily accessed. And on the other hand, the red and the yellow areas signify heavy read or write activity. These are the hotspots where most of the operations are happening. For the exam, you may be presented with a scenario where performance issues arise, and the answer might be to use the key visualizer to identify bottlenecks in the row space. So that's what this is good for. Analyzing and identifying hotspots, data distribution patterns, and performance issues. This tool can help you to visualize where certain rows are being accessed too frequently, leading to performance degradation. And so then it gives you an idea of how you need to adjust. All right. That's it on schemas, row keys, and hotspotting in Bigtable. Some aspect of this has a high chance of showing up on the exam, so make sure you understand it.